Now that we've discussed moons, on to rings. At least for me, when I think of rings, I always think of Saturn. Okay, the planet with the most notable ring system is Saturn. In fact, these were actually discovered by Galileo. Galileo first noticed them, or at least recorded them, in 1612. He then noted that they disappeared in 1613 and then came back in 1614. In some of his notes, he actually talks about it appears that Saturn has ears, which is kind of fun. Now, Christian Huygens actually was the first that we know of to suggest that the rings didn't actually disappear, that it's actually because they are very thin. So depending on the angle that we are seeing Saturn will determine whether or not we see the rings. If Saturn is tilted compared to us, then we can easily see the big, broad, beautiful rings. However, over time, as it shifts, we're going to see the ring system edge on, and it is so thin that it disappears from our view, especially if you have a low-resolution telescope. However, as it continues in its orbit, eventually we will then see the other side of the rings. Now, with better telescopes, we can tell it's not a single ring, but it's actually a system of different rings. There's a large separation through here, which is known as the Cassini division, named after the astronomer who first noticed it, or at least recorded it. It was noted that these rings cannot be made of a single solid piece. Specifically, it's because of gravity. Because of the pull of Saturn's gravity, no large solid object can stay intact. The tidal force, the pull of gravity from one side to the other, would actually rip it apart. This was then later confirmed using Doppler shift. We can see that there is a change in the speed of the rings as we get closer to a planet. Think back to Kepler's laws about how it is that things orbit around, and try and figure out if which rings should be orbiting faster and which one should be orbiting slower. Now, by looking at the spectrum of the rings, it appears that these are made of water ice, or at least particles that have since been coated in water ice. Because of that, they're very, very reflective. Water has a very high reflectivity, which is in part why it is so easy to see Saturn's rings. The particles range in size from pebbles out to boulders. I once heard somebody describe the largest of these being about the size of a school bus. Now, most of Saturn's rings are actually within the Roche limit. Previously, I mentioned that Neptune's moon Triton is going to be crossing Neptune's Roche limit in about 100 million years. The Roche limit is the distance from the planet where the planet's tidal force becomes stronger than the gravity holding an object together. So beyond the Roche limit, the gravity of the moon is able to hold itself together. However, when it crosses the Roche limit, the tidal force, the difference in gravity from one side to the other, becomes so great that the moon literally gets torn apart and then spreads out and can possibly form a ring. This is actually one likely possibility for how Saturn got its rings. There was once a medium-sized moon, for example, the size of Enceladus, that got too close, got pulled in beyond the Roche limit, and actually got torn apart. Now, during flybys of the Pioneer and Voyager spacecraft, we actually noticed there are different features within the rings. This also confirmed the Encke gap, this other region, this other gap. It also discovered the F ring, this very, very fine ring. It was also shown that all of the bigger rings, so the A, B, and C ring, also were made up of a whole bunch of ringlets. The Cassini probe, the Cassini spacecraft, was also able to take backlit views of Saturn's rings. This allowed us to get a whole new perspective. Usually when we look at Saturn, in fact, anytime we look at Saturn from the Earth, we only see the front-lit view. This is all of the light that has been reflected. With a backlit view, we're able to see how it is that the light has scattered and passed through the different rings. So in this case, the different brightnesses are telling us something about the particle size. The regions that are very, very dark must have very large particles, so these are more like boulders, because it's actually blocking a lot of the light from getting through. This really, really bright region must have very, very fine particles, like the grain of sand or dust, which is scattering the light more than reflecting it. So the Cassini division, which appears almost black and see-through as we view it from the Earth and from the front-lit side, is actually not completely empty. There's a whole bunch of relatively fine particles through there. The Voyager mission also discovered other rings, the D, E, and G rings. So the way that rings are labeled is based off of discovery. So A was first, B, then C, then D, then E, then F, then G, and so on. The D ring is actually the ring that is closest to Saturn, and some of its particles are actually falling into Saturn. This is sometimes referred to as ring rain, which is another fun name for an album. The G and E rings are actually the farthest, and they're very, very thin. The moons actually do affect the rings. In this case, the picture we're looking at is of two moons. One of these is Prometheus, and the other is Pandora. Prometheus is orbiting around by the F ring, just on the inside of the F ring, and Pandora is orbiting just on the outside of the F ring. What's notable is that the F ring is so thin and fine that it actually shouldn't persist. It should break up and dissipate over a relatively short amount of time. But Prometheus and Pandora are actually keeping it stable. As Prometheus orbits through, it pulls all the ring particles one direction. Then as Pandora comes through on the other side, it pulls all the particles back the other direction. What this does is it actually keeps the ring particles together, similar to how a shepherd and a sheepdog work together to keep the flock all together in one group. Because of this, these moons are often referred to as shepherd moons. Another way that moons can affect rings is that we can actually have a moon inside. Now in this case, these are very, very small moons. These are not medium-sized moons, and because of how small they are, we don't have to worry about the tidal force tearing them apart. But in this case, we have a very small moon that is orbiting through the ring and is actually sweeping up material, creating the Keeler gap. This has also caused a ripple, a disturbance through the rest of the ring, which you can see there. The last thing that moons can do on rings is it's possible for them to have an orbital resonance. Again, an orbital resonance is where the two pieces, usually a moon and another moon, but in this case we have a moon and a ring, where they have orbits that are even integers of each other. So in this case, for every one time that the moon Mimas has orbited around Saturn, the particles that are within the Cassini division have orbited exactly twice, which means that these particles feel the pull of gravity from the moon Mimas at the same point in their orbit every time they orbit. So this is slowly sweeping out material from the Cassini division. This is probably why we don't have a lot of large material, that it's only the fine grain of sand, piece of dust size stuff. So that was Saturn's rings, but Saturn is not the only planet to have rings. In fact, all of the Jovian planets have rings. It's just that Saturn's are the most easily noticeable. Jupiter does have many rings, but they are much smaller and darker. Because they're so much smaller and darker, it is very hard for us to see them, and therefore we don't. In fact, Jupiter's rings were not actually discovered until we sent spacecraft to Jupiter. Now, the rings around Jupiter are actually made of small and rocky material, which is in part why they're less reflective and therefore less noticeable than what we see around Saturn. Uranus's rings were actually discovered before the Voyager flybys. In this case, they were discovered during an occultation. What happens during an occultation is we see the planet actually cross in front of a star. So as we study how the starlight is dimming and changing, that actually gives us a lot of information about the planet itself. Well, as astronomers, we're looking at this occultation. So that's we're looking at the we're looking at the light curve of the star over here. What we see up this way, left and right, is the brightness of the star, and then as we go down, we're looking at time. So it starts out, we easily see all of the star, and then it blinks out, and then we see it again, and then it blinks out, and we see it, and then it blinks out, and then it is blocked by Uranus itself. And then on the other side, it kind of blinks, and then we see it, and it blinks out, and we see it, and we blinks out, and then we see it again without any more blinking. So based off of this sort of blinking on either side of Uranus, one astronomer suggested that Uranus must have a ring system to cause this sort of blinking, and that was then later confirmed by the Voyager flybys. Now, the rings around Uranus are very thin, only being a few kilometers wide. The particles that make up these rings are very small, about the size of a speck of dust, and they're also very, very dark. They're almost as black as coal. So because of those things, because they're small and very dark, we don't see them from the Earth. Now, the reason why these particles are so dark is likely due to radiation darkening. What this is the change of color because of the chemical changes due to sunlight. The particles that make up Uranus's rings are probably made of mostly methane ice, but as sunlight hits that methane ice, it breaks apart the methane and allows carbon compounds to form. So if you think about things that are rich in carbon, like graphite and coal, these are very, very dark in color. Neptune also has rings. Again, these were first discovered due to an occultation and then were later confirmed by the Voyager 2 flyby. As we look at these rings, they're actually much thinner and fainter than what we see for the other Jovian planets. In this case, we can actually see some of the rings actively dissipating. They're breaking apart right now to the point that some of the rings are not going to last to the end of the century. However, if you remember back, we mentioned that Triton is getting closer and closer, so in about 100 million years, it's going to cross the Roche limit. And when it does, it is going to get torn apart and turn into a new, spectacular ring system. So we mentioned already how Saturn got its rings. It is likely caused by a moon getting torn apart as it crossed the Roche limit. However, that doesn't explain the rings for Jupiter, Uranus, and Neptune. In this case, we think that it is likely caused by meteorite impacts on the small inner moons. So the idea is that we have the moons, which, when they get hit, can actually throw out debris, and over time, that debris will collect together, forming into a ring system. This is our best guess to why Jupiter, Uranus, and Neptune have rings. Alright, here is our fifth and final question for this series. The rings of the Jovian planets, A, are made of one solid sheet of ices around the planet, B, are made of pieces of rock and ice that range from the size of pebbles to boulders, or C, are an optical illusion due to reflections from the atmosphere. Go ahead and think about it, and we'll discuss in just a bit. Alright, so the answer is the Jovian rings are A, made of pieces of rock and ice that range in the size of pebbles to boulders. The correct answer is B. They are made of pieces of rock and ice.